Many times in the real world, scientists are interested in being able to recreate the results of an experiment and investigating how to undo the steps they followed. This process involves the application of inverse functions, and that's what we'll be examining today. Hi, my name is Tom Atwater, and in this lesson we will explore logarithmic and exponential functions. Let's start with a definition. Definition of a one-to-one function. A function f is one-to-one on a domain D if f of a does not equal f of b whenever a doesn't equal b. Let's look at some graphs that will help illustrate this definition. We have the graph y equals the absolute value of x. And it is this black line, which you can see a red line going through it. We're going to use something called a horizontal line test. The horizontal line test shows us that as you draw this horizontal line, you'll see that it intersects in two places. And when that occurs, what it means is that this function is not one-to-one. If we look at y equals the square root of x, you'll see that the horizontal line intersects at only one place, in which case this function is one-to-one. Okay, so one of the things about the one-to-one function is this, that when you put an input in and you take an input out, if we reverse that, we can put the output back into a function. We'll just get one input from it. And when you do that, you are doing the inverse function. Now, the symbol for inverse function of f is this. Which we read as f inverse of x. Now that -1, you don't read it as an exponent. It's not an exponent. This is f inverse of x. The result of composing a function with its inverse in either order, that is f of f inverse of x or f inverse of f of x, is the identity function x. In other words, if I have two functions, f and g of x, and I compose them together, and I get the result x, and then I do the same thing, but I go with g of f of x, and I get x, that means that the two functions, f and g, are inverses. Now, let's look at how we can find an inverse function for a function that's one-to-one. Writing an inverse function. First step, solve the equation for x in terms of y. And then interchange x and y, and the resulting formula will be that y is equal to the inverse function. Okay, I think it's best to look at some examples to see how this works. Find f inverse of x and verify that the two functions are in fact inverse functions for the function f of x is equal to x cubed minus 1. All right, so we're going to take the function f of x equals x cubed minus 1 and replace f of x with the letter y. So our equation would become this: y equals x cubed minus 1. And then what we want to do is solve that equation for x in terms of y. So we would have x cubed equals y plus 1, and then x would equal the cube root of y plus 1. And the second step is to replace x with y and y with x, so we get y equals the cube root of x plus 1. And if you verified that, that is to say, if you did this function, which is the inverse function, so we'll write that f inverse of x equals the cube root of x plus 1. If we were to compose the two functions together, f with the inverse and then do the other way around, the inverse with the function f, you would see that these are in fact inverse functions of each other. Let's try another example. Find f inverse of x and verify that they are in fact inverses for the function f of x equals 2x plus 1 divided by x plus 3. Okay, so we'll start off again replacing f of x with y. So our equation looks like this. Y equals 2x plus 1 over x plus 3. And what I need to do here is to solve that for x in terms of y. So we multiply by x plus 3 on both sides. It cancels out here, and over here we get x, y plus 3y equals 2x plus 1. And now what I want to do is get all of the terms that have x's on one side. So I need to bring the 2x over, and let's bring the 3y over here. So we get x, y minus 2x equals 1 minus 3y. And now what I need to do is factor out the x, which would give me x times the quantity y minus 2 equals 1 minus 3y. And then the next step would be to divide by y minus 2. So I'm going to get x equals 1 minus 3y over y minus 2. And my next step is to replace the x with y and the y with x, so that we get the function y equals 1 minus 3x over x minus 2. And that's my inverse function. F inverse of x would be equal to 1 minus 3x over x minus 2. Once again, if you take and compose the inverse function with the original function, then you will find that that in fact gives you the identity function, which means that these two are inverses of each other. Well, now let's turn our attention to logarithmic functions. The definition base A of a logarithmic function. The base A logarithmic function, y equals log base A of x, is the inverse of the base A exponential function, y equals a to the x, where a is greater than 0 and a does not equal 1. The domain of y equals log base A of x is from 0 to infinity, which is the same as the range for y equals a to the x. The range of y equals log base A of x is equal to negative infinity to infinity, which again is the domain of y equals a to the x. Now, since composition of inverse functions can go in either order leads to the identity function, we have the following inverse properties for those functions. Starting base A, we have a raised to the log base A of x. So a raised to that exponent will give us back x, which is the identity function. And similarly, if we have log base A of a raised up to the x, that's going to give us back x because, again, we're just composing a function with its inverse. This is true for a being greater than 0 and a being greater than 1 and x being greater than 0. Well, what about for a specific base, the base e? In that case, if you have e raised to the log base e of x, you'll get back x because that's a function with its inverse. And similarly, if you have log base e of e raised to the x, you will get back x. And that's for x being greater than 0. All right, let's try an example. Solve for y where you have log of y is equal to 2t plus 4. Recall that this is the natural log, which is the same as saying log base e of y. So what we're going to do here is raise the base e to both sides of this equation. In other words, we're going to write e to the log of y equals e, let me erase that, equals e raised to the 2t plus 4. And so when you raise e to the natural log of y like this, what you'll get is just y, because it's a function composed with its inverse. On the other side, we have e raised to the 2t plus 4. And so that gives us the value of y. Now, there are three other properties of logarithms that we need to review. So let's take a look at them now. For any real numbers, x being greater than 0 and y being greater than 0, we have the product rule. And the product rule tells us that if you take the log of x times y, that's the same as adding the log of x plus the log of y. We also have the quotient rule. The quotient rule tells us if we have log of x divided by y, that's going to equal the log of x minus the log of y. And finally, we have the power rule, which tells us if you have log base a of x raised to the power of y, that's equal to y times log base a of x. That is, you take the exponent down in front of the logarithm and multiply them. All right, I think the best thing here would be to look at an example of using the inverse properties to solve an equation. Solve the equation algebraically. And then we have 1.045 raised to the t, and that's equal to 2. And so what we will do is we'll take the log of both sides of this equation. So, and I will use the natural log. So 1.045t equals natural log of 2. Now, the power rule tells us that we can take the t and bring it down in front of the natural log. So we're going to have t times the natural log of 1.045, and that's going to equal the natural log of 2. And then finally, to isolate t, we have to divide both sides by the natural log of 1.045. So our answer would be the t is equal to the natural log of 2 divided by the natural log of 1.045. So that's how we can use logarithms to solve exponential equations. Now, finally, we want to look at a formula that will allow us to change the base of a logarithm to a different base. So, change of base formula. So we have log base a of x, and that is equal to the natural log of x divided by the natural log of a. And we pick changing to the natural log because it is convenient to use the natural log. It is on your calculator as its own independent button, so it's much easier to choose that. However, I do want to tell you that you could use any base over here, as long as you use the same base on top as you do on the bottom. So let's take an example where we have to use the change of base formula. Draw the graph and determine the domain and range of the following function. Y equals log base 2 of x plus 1. So the first thing that we're going to want to do is to take this equation and rewrite it using that base change formula. In other words, what we have is that y is going to equal the natural log of x plus 1 over the natural log of 2. And so the natural log of 2, of course, is a constant term, and we can plug this into our calculator, into the equation editor, where we have y sub 1 would equal this, and graph it. And when we do that, we get this graph right here, which shows the natural log of x plus 1 divided by the natural log of 2. So what about the domain? Well, the domain, and it's on the graphing calculator, it doesn't show you this, but what we have here is a vertical asymptote coming right down through -1. So the domain is from -1 up through infinity. Domain, -1 to infinity. And neither one is included in that. The range, of course, this continues down the graph, and so the range is from -infinity to +infinity. All right, so that's how the change of base formula can help us, because we could plug it into the calculator, have it graph drawn for us. Well, now it's time for you to try a problem. So let me advance to the problem. I want you to draw the graph and determine the domain and range of the function y equals log base 2 of x. Pause the video while you work on this problem. And when you're finished, restart the video to check your solution. All right, let's find out how you did. The first thing you want to do is rewrite y equals log base 2 of x using the change of base formula, so that we get y equals the natural log of x divided by the natural log of 2. And now we can plug that into the calculator and have the calculator graph it for us, and it would give us this graph right here. Once again, you can see that you have a vertical asymptote here. So this graph that you just had the calculator graph for you is the same graph I had shifted over to the right one. Okay, great. In this lesson, we started off by exploring inverse functions, and then specifically went into logarithmic functions and exponential functions. Now, be sure to work the exercises that your teacher assigns, and we'll see you next time.